In section 13.1, we worked on our understanding of functions of multiple variables. For the rest of this chapter, we're going to focus on understanding how to apply calculus to functions of multiple variables. And 13.2 is going to focus specifically on limits and continuity. Both of these topics are topics that we saw back in Calc 1 and continued working with them in Calc 2. But again, now what we're working with is functions of multiple variables. So how adding additional dimensions is going to affect our understanding of both limits and continuities. So first of all, I have a remark to start here that very similar to Calc 1 when we're working with functions of one variable, if your particular function f is defined at a given point x naught, y naught, z naught, or if it can be simplified so that it can be defined at that point, then we can physically just plug and chug that value in there and get out our function value. I have written this statement in 3 dimensions, but it also holds down in 2 dimensions. So for number 2 here, we want to compute the limit. Can we just plug in 0, 0 for x and y in each case? Sure, so in this particular example, we have 4 times 0 minus 0 divided by sine of 0 minus 1. So what we get here is 0 over negative 1, which is 0. All right, it's as easy as that. Let's take a look at number 4. We can just evaluate this, e to the 2 times 1 minus negative 3 squared, which is e to the 2 minus 9, or e to the negative 7. This is defined, and so this is our limiting value. For 14, if we try to evaluate at 0, 0, then what we get here is 0 on top and 0 on bottom. So I'll just make a note here. We know from our experience in Calc 1 that 0 over 0 is indeterminate. So we need to do some work here in order to simplify. And so what we recognize is this numerator is a difference of squares. So I'm going to begin by writing my limit here in front, and then factoring that numerator to an x squared minus 4y squared and an x squared plus 4y squared. Then on our denominator, we still have our x squared plus 4y squared. We can cancel those common factors because those are equal to 1. And then finally, we can plug 0 in for x and 0 in for y, and that's going to give us a limiting value of 0. All right, so these are examples of limits that we can compute directly by either plugging in our limiting values for x and y, or by simplifying first, in this case, factoring in problem 14. All right, so how are limits going to different in 2 or 3 dimensions from what we understand in limits in 1 dimension? So I have here, recall that for functions of one variable, we have one-sided limits. We talked about how we can approach an x value from the right or from the left. So there are 2 ways to approach a point. Geometrically, we can illustrate this with just a generic function. So just draw some function, doesn't matter what it looks like, and we'll call this function f of x. And then pick some point here along the x-axis, we'll call it x naught. And so if we map it up, here is the point on the function. If we come from the left, we have the limit as x approaches x naught from the left, or we can approach from this way, the limit as x approaches x naught from the right. And those are our only 2 options, right? If we're talking about a curve, which is a one-dimensional curve in 2 dimensions, there are only 2 ways to get to a point. So it's very clear we say that a limit exists if the left and right-hand limit agree at that point. Things get a little bit hairy when we introduce additional dimensions. So if we look at this, a function of 2 or 3 variables, we no longer have a clear-cut way to approach a point. So as an example, let's suppose that we have a paraboloid. All right, so I'll just draw a little paraboloid here. And let's suppose that we have a point on our paraboloid. So now that instead of a point on a curve, this is a point on a surface. We don't have this notion of a left or right hand limit, right? Maybe we could approach coming this direction, or maybe we're going to squiggle towards this direction, or maybe we're going to come around the paraboloid here, right? There are infinitely many ways to approach this point. This is very problematic. It was very cut and dry in one dimension that we check from the left and from the right, and as long as those two agree, bam, we know that our limit exists. So how are we going to reconcile this in higher dimensions? So Theorem 2 is going to talk about how we understand the behavior of a limit when we're approaching from different directions. Part A says, look, if your function has a limiting value of L as xy approaches x naught, y naught, then it shouldn't matter what way you approach that point, that limiting value is going to be the same along any smooth curve. All right? So conversely, if your limit of f of x fails to exist along some smooth curve, so you happen to pick some curve and your limit does not exist, or if you have two different limits along two different smooth curves, then you say that the limit of that function does not exist as you're approaching that particular coordinate point. So the reality is, when we look at this theorem, it's actually going to be really difficult to prove that a limit does exist, because there's no way we can possibly check every smooth curve. Now, if it's one of these easier examples, like from 2 to 14, these ones that we saw earlier, where it was plug and chug or simplify and plug and chug, then yes, we can prove that the limit exists. But just picking a couple of different curves and getting the same limiting value is not enough, because what if you didn't pick the correct curve? So oftentimes we'll be looking at part B and we're going to say, what smooth curve could I choose that's going to give me two different limiting values? Because then I can conclude by Theorem 2 part B that the limit does not exist. All right, so I have some examples here for you. Notice that this is labeled A. This is not pulled out of our textbook, but I wanted to give you additional examples where the limit does not exist. So for problem A, we're approaching 0, 0. You'll notice here that if I try to evaluate, I get 0 over 0. And if I try to factor, I could factor the numerator to x plus y, x minus y. That's really not going to be helpful here, because it's not going to simplify with anything on top. Now, students oftentimes are like, oh, 0 over 0, I want to use L'Hopital's rule, which is great in functions of one variable because the derivative is well defined. But if you want to apply L'Hopital's rule here, what do you mean by the derivative of the top or the derivative of the bottom? We have two different variables. So what are you taking the derivative with respect to? So just as a note here, we can no longer apply L'Hopital's rule. All right, and this is due to the fact that we have multiple variables involved. So while L'Hopital's rule was really glorious in Calc 1, we kind of have to throw it out the window. So instead, what we're going to do is we're going to choose, very wisely, various curves that go through this point 0, 0. And we hope that along different curves that we get different limiting values. Again, leaning on the result of part B. So what's super important is that you make sure that your curves go through this point. Otherwise, they're not appropriate curves to look at. So let's let xy approach 0, 0 along the curve. And I'll put that in quotes because I'm actually going to choose a line, but along the curve x equals 0. In other words, along the y-axis. So what happens when I approach the origin along the y-axis? What happens to my limiting value here? So I'm going to do the following. This is different than the book notation. So I want to be very clear. I feel like the book doesn't handle these situations very well. So I'm going to introduce kind of a different way to look at these problems. I'm going to let f of x, y denote that function inside the limit. So in this case, x squared minus y squared over x squared plus y squared. All right, now I want to look at x equals 0. So if x equals 0, then we're looking at the function f of 0 comma y. So wherever I saw an x, I'm now plugging in 0. So this becomes a function of one variable, which is negative y squared over y squared, or in other words, it's just the constant function 1. So what this tells me is, since I know the limit of a constant is a constant, I have that this function is approaching negative 1 as xy is approaching 0, 0 along the line x equals 0. All right, so here's one of my limiting values. Let me just box that in red to kind of draw our attention to it. All right, here's one limiting value. Does this mean that the value of the limit is negative 1? No, it just means that along this particular curve that I chose, the limiting value is negative 1. So let's see if we can pick another curve. I'll maybe label this 1 and 2. Let's pick another curve that we hope is going to give us a different limiting value. So now let's look at xy approaching the origin along y equals 0, or in other words, the x-axis. All right, what's going to happen here? So now I want to take my function and I want to see what happens when y equals 0. So this gives me x squared minus 0 over x squared plus 0. In other words, this is f of x equals x squared over x squared, which is 1. All right, so that being said, what we have is a new constant function, and the limit of a constant is a constant, so we know that this limiting value is approaching 1. F of xy is approaching 1 as xy is approaching the origin along y equals 0. So again, let's box that in red to grab attention. What we have just found is two different limiting values along two smooth curves, or in this case lines, that goes through our limiting coordinate point 0, 0. This is bad, right? So we can conclude here by theorem 13.2.2 part B, the limit does not exist. All right. Now, when you're first working through these problems, it might not always be clear what the correct curve is to look at. I always recommend looking at x equals 0 and y equals 0 just because they greatly reduce your, they greatly simplify the function inside, but sometimes they'll give the same limiting value. So then you have to start getting creative and choosing other curves that happen to pass through your limiting xy coordinate point. All right, let's take a look at B. Same instructions. We want to show that this limit does not exist. So I'm going to start off here. Whoops, let's get back to black. I'm going to start off here by defining f of xy to be that inner function. All right. And kind of sticking with what we did in the previous example, let's look along the curve x equals 0. All right, what's going to happen here? So that's going to give me f of 0 comma y, which is going to be 0 over x, whoops, not x squared, 0 over 0 plus y to the 4th. So this is 0 over the y to the 4th, which is 0. All right, so this function zeroed out, and that tells me that f of xy is approaching 0 as xy is approaching 0, 0 along x equals 0. All right, I'm going to write this in blue because I don't necessarily want you to write this down. But just as a quick note here, if we tried to go along y equals 0, what's going to happen? F of x 0 is going to be 0 over x squared plus 0, which is also 0. I'm putting a frowny face here because this is bad. We happen to get two of the same limiting values, but this does not mean, so I'll put here, this does not imply that the limiting value is 0. Rather, it just means that we happen to pick two curves along with which the limiting value is 0. But remember, that theorem up above says that the limiting value is the same along every single curve. All we have shown is that two curves have the same limiting value, so you need to keep checking, right? And there's no way that we can check infinitely many curves that approach this point. So we need to be sneaky here. We need to think of some appropriate curves that will hopefully give us a different value for our limit here. So as I'm looking at this function, I'm noticing that I have a y to the fourth on bottom and an x squared. I'd like to be able to combine those terms, but right now they have different powers. So if I just was able to square that x squared term, that would really make things a lot easier. So let's instead, for our second curve, I'm going to strategically choose that x equals y squared, so that when I plug it into this term down here, x squared becomes y squared squared, or y to the fourth. Now again, it's very important to note that this curve passes through the point that we're looking at. Right? So if it didn't, then it wouldn't be an appropriate curve to consider. All right, so keeping this in mind, f of y squared comma y, which I'll just denote as f of y from here on out, is going to be y squared times y squared over y to the fourth plus y to the fourth. So this is y to the fourth over 2y to the fourth, which is 1/2. All right, so this tells me that my function is approaching 1/2 as xy approaches the origin along x equals y squared. All right, so getting out my red marker here, I have a limiting value of 1/2 here, and I have a limiting value of 0 here. So that's enough, right? We can say by Theorem 13.2.2 Part B, the limit does not exist. All right, we were able to strategically choose two curves, both of which pass through our limiting xy coordinate point, but curves that gave us two different values for our function f of xy. So again, B was a good example where the coordinate axes weren't good enough, right? We had to toss this out because it didn't give us a different limiting value than what we had already found. All right, we have one more example here, and this one is pulled out of the text, problem 8, part B. Again, we're approaching the origin. This just is a fluke that we're approaching the same point, but we could do limits approaching a different point. We have cosine of xy over x squared plus y squared. All right, so what's happening here? At this particular problem, we can actually evaluate this directly. So if we just plug in our limiting points, we have cosine of 0 times 0 all over 0 squared plus 0 squared. So cosine of 0 is 1, and on bottom we have 0, and this is enough to say that this limit does not exist. But in fact, we could reduce it down to just one variable if we want. Let's look along x equals 0 so that we get it down to a function of one variable. This would give us f of 0 comma y equals cosine of 0 divided by 0 plus y squared. So this is 1 over y squared. So now the question becomes, what is the limit as y approaches 0 of my f of y function? So this is the limit as y approaches 0 of 1 over y squared, which is 1 over 0, which does not exist. So we just found in one dimension a curve that passes through the origin, 0, 0, in which this limit does not exist. So again, by theorem 13.2.2 part B, we say that this limit does not exist because we found a smooth curve through 0, 0, through which that limit of a single variable function does not exist. All right, just a remark here on this next page. The book has a lot of does not exists in the back. All right, and this is because the book is now assuming that if your limiting value is infinite, it's going to say that the limit does not exist. I'm not a big fan of this notation or this approach because earlier in the textbook, when we're in Calc 1 and 2, plus or minus infinity is a very reasonable value for your limit. So suddenly now they're deciding that it's not reasonable and they're calling that does not exist. So as a note here, I will accept does not exist or plus or minus infinity as correct answers if that happens to be the case. So just wanted to make a note on that. I also have a remark here that it may be helpful to switch to polar coordinates or spherical coordinates depending on the setup of your particular limit. So we spent a lot of time in section 11.8 really understanding those two different coordinate systems. And this is the first time where we're applying it outside of that section. So let's take a look at problem 24. Evaluate the limit by converting to polar coordinates. So we have the limit as xy approaches 0, 0 of y times the natural log of x squared plus y squared. So if you'll recall, we have the equation that r squared equals x squared plus y squared. So we can plug that in inside the limit, or excuse me, inside the natural log. And we also have that y is r cosine theta. So now we know how to transform inside the limit. How would we transform these little subscripts on our limit? So if we know that xy is approaching 0, 0, then what must be true? So if y is r cosine theta and x is r sine theta, the only way that both of those could be approaching 0 is if r is also approaching 0, because both sine and cosine cannot equal 0 at the same time, right? They're shifts of one another function-wise. So what I'm saying here is that this implies that r is also approaching 0. And furthermore, we're only approaching it from the right because remember, we're assuming that r is always non-negative in polar coordinates here. All right, so let's take a look at what this new limit is going to look like in polar coordinates. So we're now going to write this as the limit as r approaches 0 from the right. Our y value is going to become r cosine theta. And then we have the natural log of r squared. Now, one thing that I want to note here is that the cosine function is bounded. So cosine is bounded between 1 and -1. So we know that it's not, for example, blasting off to infinity. We know that it's bounded and it's finite. So what I have here is this term is tending towards 0 because r is going to 0 and cosine is a finite number between -1 and 1. What's happening to this term? Remember, think of the natural log function. As r tends to 0 from the right, our natural log function dies off to -infinity. So this is of the form 0 times infinity. That merits a sad face, right? Because 0 times infinity is an indeterminate product. And so we need to do a little bit of work here. what I'd like to do is push one of these terms to the denominator so that I can then use L'Hopital's rule, because after all, this is a single variable limit. There happens to be a theta in there, but that theta is just a constant and I can pull it out front if I want. So what I'm going to do is I am going to take this, oh goodness, I just noticed that I used the incorrect trig function. So do please correct this. I'm going to write it in red here. Y should be sine and X should be cosine. So this guy should have been sine. Nothing that we did is incorrect. I just used the wrong trig function. All right, so what I'm going to do here is I'm going to pull that trig function out front because the limit does not depend on theta. And then I'm going to take this r and I'm going to push it to the denominator. So I have the natural log of r squared on top. If I push r to the denominator, I pay for it with the reciprocal. So I'm going to make it a 1 over r here. So now what's happening? My numerator is tending to negative infinity. My denominator is going to positive infinity, and I can now apply L'Hopital's rule here. So I'm going to write a little L apostrophe H to indicate that I'm going to use L'Hopital's rule. I still have my sine function out front. I still have my limit as r is approaching 0 from the right. All right, so the derivative of the natural log of r squared is 1 over r squared times the derivative of r squared, which is 2r. And then the derivative of 1 over r, that's an r to the negative 1, so this becomes negative 1 over r squared. So let me multiply by the reciprocal, which is going to cancel these r squareds out. And what I have is sine of theta times the limit as r is going to 0 from the right of negative 2r. So again, remember that sine is bounded between plus and minus 1. And this term is going to 0. So I get sine of theta times 0, which gives me a limiting value here of 0. All right. So here we just saw an example of why polar coordinates might be useful in this context. We want to end this section by talking about domains of continuity for multivariable functions. All right, so we say that a function f of x, y is continuous at a point if that limit as x approaches x naught, y naught of the function is equal to the function value f of x naught, y naught. So this is very similar to the definition of continuity that we use in Calc 1. In addition, if it's continuous at every point in an open set D, we say that it's continuous on D. And if it's continuous on the whole plane, we say that the function's continuous everywhere. Now, I'm going to assume basic knowledge of continuity of functions that we learned from Calc 1. So in particular, we know that the composition of two continuous functions is also continuous, as is the sum, difference, or product of continuous functions. And quotients of continuous functions are also continuous, assuming that the denominator is non-zero. And so here's a pile of functions that we know to be continuous. Polynomials are well behaved and they're continuous everywhere. Both trig and inverse trig functions are continuous on their domains, so just make sure you know their domains. Exponential functions are continuous everywhere. Radicals are continuous for positive values. Logarithmic are continuous for positive values. And then radicals are continuous on their domains. If they're odd radicals, they're continuous everywhere, because you can, for example, take cube roots of negative numbers. Even radicals are continuous for non-negative numbers. And then finally, rational functions are continuous everywhere where the denominator is non-zero. So using this knowledge that we know from Calc 1, what we would like to do is sketch the domain of continuity. So sketch the largest region on which f is continuous. So let's take a look here. On 41, we have f of xy is y times the natural log of x plus 1. So this y, we have no issues. We have no division by 0, no restrictions on this y value. So y can be anything. But let's take a closer look at this natural log function. We know that the natural log of y is continuous if y is strictly greater than 0. So in the case of the natural log of 1 plus x, we know that it's continuous if 1 plus x is positive. In other words, if x is greater than -1. So y can be anything. X needs to be greater than -1. Let's go ahead and sketch this region here in the plane. So x equals 1 is right along here, and I'm making it dashed because I don't want to include 1. So this means I'm not including -1. And then I want to shade everywhere where it's greater than -1. All right, so we're dividing the plane up here into basically two pieces. X values less than -1 and x values greater than -1, and we want to shade the areas where x is greater than -1. All right, so we have two more examples of finding domains of continuity. All right, 43, we have this rather ugly looking function. On top, I'm just going to write a check mark. The top is a polynomial, so it's defined everywhere for all x and y values. All right, on bottom, we have a square root. Now, normally, I just want everything underneath the square root to be non-negative, but I actually want to exclude 0 here because I don't want to divide by 0. So we need for 25 minus x squared minus y squared to be strictly greater than 0. Again, we don't want to divide by 0, so we're going to exclude 0. So another way to say this is that 25 is greater than x squared plus y squared. Well, I know x squared plus y squared equals 25 to be a circle centered at the origin of radius 5. I want all values where x squared plus y squared is less than 25. So let me plot that circle going out 5 in every direction. I'm going to make it dash because I don't want to include points where the radius is equal to 25. And I want to include all points whose radius is less than 5 away from the origin. So that means I'm going to shade inside the circle and not outside the circle because I want to be less than 25. All right, so in words, I want to be inside the circle of radius 5 centered at the origin. All right, so there's 45, or excuse me, 43. And for our last example for this section, we have a sine inverse function here. And so we really need to think back of our knowledge of inverse trigonometric functions. Remember that the range of sine x is from -1 to 1. So that tells me that the domain of sine inverse of x is from -1 to 1. All right, so we mentioned that inverse trigonometric functions are continuous on their domains. So what we need in this particular case is we need that xy is between -1 and 1. All right, so this is sneaky here because we would like to solve for y in the middle, but we don't quite know if x is positive or y is positive. And similarly, we don't know if x is negative or y is negative. So what I'm going to do here is I'm going to split this up into two different inequalities. Let's look at that xy as a product is positive, or I should say non-negative. So either both x and y are positive or both x and y are negative. So let's break this up. First case is if we're in quadrant 1, then both x and y are positive. So what this means is if I divide all three pieces of my inequality by x, I'm assuming x is positive, so it's not going to switch my inequalities. I have 0 is less than or equal to y is less than or equal to 1 over x. So if I plot this, I want to go through 1, 1, 1/2, 2, and 2, 1/2, and so on and so forth. I am making this a solid line because I want to include points on this line. And the question becomes, do I want to shade inside or outside of this curve in quadrant 1? So let's just pick this point 2, 2 and see if it satisfies this inequality. So if I plug in 2 for y and 2 for x, it would say that 2 is less than or equal to 1/2. That's not true, so I'm going to shade on the other side of this line. That is this inner part. Remember, I'm only looking at the first quadrant right now. All right. So now our other option when we're looking at this inequality is that both x and y are negative such that their product is positive. So that would be in quadrant 3, both x and y are negative. So why do I care about this? That's because when I divide all 3 pieces of my inequality by x, I now need to switch the sign, right? I need to switch the inequality because I'm dividing by a negative. So this becomes 0 is less than or equal to y is, or excuse me, greater than or equal to y is greater than or equal to 1/x. All right, so let me plot this reciprocal function here in the third quadrant. And again, let me test a point, -2, -2. So if I plug this point in, what I would get is -2 is greater than or equal to -1/2. And that's simply not true, right? -2 is smaller than it. So I need to shade on the other side. All right, and we can continue this process onward. So now I'm going to look at the other inequality, which is -1 is less than or equal to xy is less than or equal to 0. We are now assuming that the product of these two numbers, x and y, is negative. So we're either in quadrant 2 or quadrant 4. So in quadrant 2, x is negative and y is positive. So when I'm dividing through by x, I need to switch my inequalities. So I get -1 is greater than or equal, -1/x is greater than or equal to y is greater than or equal to 0. So let me plot this function in the second quadrant. And using my same approach, this is the point -2, +2. Let's plug it in and see if it satisfies the inequality. So that would give me a +1/2 is greater than or equal to a +2, which is false, right? So I can't shade on that side of the line. I have to shade on the other side of the line. All right, and as you can imagine, you can do a similar argument here for the fourth quadrant, and I think we all believe that the same thing is going to happen here. You just need to be very careful as to what assumptions you're making about the signs of your variables x, y. All right, so what I have shaded here in blue is going to be the domain of continuity for this function f of x, y. So kind of this star-shaped area in and around the origin. All right, so this concludes our notes for section 13.2. In the next section, 13.3, we will talk about how to find derivatives of multivariable functions.